All right, so now we move into electronegativity and bond polarity. Okay, we talked about how things get shared, how things are going to be shared, and we're going to talk about how sometimes, yes, they're sharing electrons or they're going to one side, they're not going to be equally shared. Okay, we're going to talk about electronegativity. We hinted before on one of the periodic tables. The trend of electronegativity we're going to see as we go from top to bottom, electronegativity is going to decrease, meaning the lithium is going to be the most electronegative. As we move to the right of the periodic table, groups, you're going to see electronegativity increasement. Okay. The most electronegative thing, electronegativity or electronegative atom we have is fluorine. And we'll talk about how that is actually going to affect molecules when they come together. So what is electronegativity? Electronegativity is the value of an element that indicates the attraction of the atom for the shared electron it is bonded. So pretty much what atom is going to be more attracted to those electrons they're sharing? Which one is going to be pulling it to one side or to the other side? There are some exceptions that sometimes they're going to be shared equally. So that's not a problem. Increase from left to right going across the periodic table, increases from the bottom to the top of the periodic table. Is high for nonmetals, with fluorine being the highest, and low with metals. Metals have low electronegativity, but nonmetals are going to be the ones on the side that is going to be more electronegative. In nonpolar covalent bond of hydrogen, electrons are shared equally. In polar covalent bonds of HCl, electrons are shared unequally. So this is where it gets a little bit interesting, okay? Here we share through the same, they're going to equally share electrons. But when we start going into a hydrogen and we replace it with a chlorine, here we go. That is a problem. But a chlorine is going to be more negative and it's going to pull the electrons into that direction, okay? Causing what we call an electrodeficient atom, okay, or the electrodeficient element. And we'll talk about how that actually affects. That is very important in our chemistry. Can you do it mathematically? The answer is yes. Can we calculate? Yes. What you're going to do is you're going to focus on two particular atoms. So here we have two particular atoms. We have two nitrogens, okay, sharing. What we're going to see is we're going to take the electronegativity of hydrogen that is going to be 3.0, and you're going to subtract 3.0 because they're both 3.0 and we get 0. A 0 indicates non-polar covalent bond. Okay, so let's mix now a bromine with a nitrogen. Okay, nitrogen and a bromine. If we subtract, we have 3.0, 2.8 is 8 from the bromine. Okay, this is where I'm getting those numbers. 3.0, 2.8, we subtracted. Yes, there's a little difference, 0.20, but it's too negligible. Okay, so it's going to be non-polar covalent. Here we have another example, 2.1. Okay, 2.1 phosphorus and 1.8 silica. Okay. If we look at this particular one, so phosphorus silica, we subtracting is going to be 0.3. It's still non-covalent. Let me go over some examples when we start seeing what we call polarity. Okay, where the difference is going to be different. So we have a 3.5. 3.5, there is going to be an oxygen and a nitrogen. Okay. On this particular is going to be a oxygen and a nitrogen. We subtracting, that is when we start seeing a difference. 0.5. Anything above 0.5 is going to be considered covalent. Okay? It is going to be, it's going to be considered polar covalent. So a polar covalent bond is when it occurs between nonmetals, is unequal share electron, has a moderate electronegativity difference. So it's going to be 0.5. That is going to make this polar covalent. What does that mean? That the arrow is going to be pushing in that direction. Okay, that is going to make it a polar covalent. Let's do another example. We're going to do 3 and 2.5, carbon, nitrogen. Okay, we're going to do a carbon and a nitrogen. Nitrogen is 3, carbon is 2. That's going to be 0.5. So that is going to be polar because it's 0.5. Now let's go between a 3.5 and a 2.5. Okay, sulfur and oxygen. If we look at this, we subtract them, it's going to be polar. Okay, the difference is 1. So anything between 0.5 to 1 is going to be polar covalent. Okay, anything between 0.0 to 0.3 is going to be nonpolar. So what is this? What is this difference in the in covalent electronegativity going to cause? I already hinted, okay? The arrow I drew, there's a reason why I drew the arrow. The arrow is going to indicate a couple of things. So a polar covalent bond becomes more polar as the difference in electronegativity increases. The separation of charges in the polar bond is called a dipole. Again, that's what I was looking for, a dipole. The positive end and the negative ends of the dipole are located by using a lower Greek letter delta. Okay, either going to be negative or positive. Okay, so delta negative means that that's going to be the most electronegative atom. Delta plus is going to be what we call the electrodeficient or positive atom. So with a positive and a negative charge, the arrow points from the positive, the tail, to the negative end of the dipole. So that's where we're going to create a dipole moment. Why do we care about this ones? We care because this is going to make certain solvents, certain molecules, polar or non-polar. And it's going to affect the properties of being able to dissolve stuff or not being compatible. When you try to dissolve a liquid in another liquid, it's going to require it to be polar, dissolve polar, non-polar, dissolve non-polar. And how can we tell? We could tell by calculating electronegativity. Ionic bonds, okay? Ionic bonds occur when metal and a non-metal ions. This is a result from electron transfer. It has a large electronegativity difference. Those are considered even higher. Okay, here chlorine has 3.0. Potassium has 0.8, and that is going to be 2.2. That is no longer polar covalent, is in the levels of ionic. Okay, here we have 2.1 is going to be ionic between the sodium and nitrogen and the sodium. It's going to be 2.1 is going to be ionic. Okay, ionic is a lot more stronger. Okay, ionic is a lot more stronger. Is the difference in electronegativity values of two atoms can be used to predict the chemical bond. If the electronegativity difference between 0 and 4, the bond is non-polar covalent bond. Okay, I know I said 3. Usually it's hard to measure a 0.4, but 0.4 is the borderline. Anything between 4 and 5 to 0.8 is considered a polar covalent bond. Anything between 1.9 to to 3.3, the bond is considered ionic. So by measuring electronegativity, we can actually tell what kind of bond it is. Okay, is it a non-polar covalent bond, a polar covalent bond or ionic. So here we have nonpolar covalent, polar covalent, ionic. Okay. Electron share inequality. So here we have electron share, polar, nonpolar covalent bond, they're going to share equally. When we have polar covalent bond, we're not going to be sharing. One is going to take most of the electrons. And when you have a 1.923, it means that we had an electron transfer. Okay, there's no sharing. One of them took it to one side already. Here's some other examples. Hydrogen is 0. Electronegativity is 0. Type of bond is a non-covalent bond. Br and CO minus are very similar. So again, 0.2 non-covalent bond. Once we hit right here, hydrogen and bromine, that's what we call a polar bond. Okay, HCl, and this is wrong. This should be lowercase l. So it's 0.9 polar covalent bond. NaCl, it is going to be ionic. Okay, magnesium oxide, it is going to be ionic. Okay, so that's the reasoning how we could tell if something is polar or non-polar by calculating the particular covalent bonds. Okay, now we move into something that gets interesting. Remember I told you that we have to be careful with shapes of the molecules. Lewis-Dot structures are good. It's the beginning, but now we have to put shapes. Shapes in molecules are very important. Okay, they are going to give us certain insights and certain geometries and certain things that are important properties that we have to deal with. Example, in the molecule methane, the central atom is going to be carbon. It's bonded to 4 hydrogens atoms. We talked about in Lewis-Dot structure why. But now we have to be careful. We have to deal with the geometry. We haven't paid attention to geometry. And geometry is going to be the geometry that gives the minimal repulsion for the methane, for the carbon, is going to be tetrahedral with bond angles of 109. Okay, it's not going to be this type, the Lewis structure. They're not going to be that type. It's going to be the one, the tetrahedral. They're going to be 109. They're going to reduce what we call repulsion. Okay, between the electrons here, 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 and here. Okay, and we'll talk about a little bit more of that. That's what we're going to be focusing for the rest of this chapter. The valence electron shell pair repulsion theory describes the orientation of electron groups around the central atom. Very important. States that groups that are arranged as far as possible around the center atom. So that's what we're going to be surrounding them. States that a specific shape of molecules is determined by the number of atoms attached on the central atom. Central atoms with 2 electron groups. Okay, so here we have a center atom that has 2 electron groups. So we have a molecule, carbon. We already drew the Lewis-Dot structure for this one. It is going to have that one. 2 electron groups are placed around the central atom on the carbon. The repulsion is minimizing by placing the 2 groups opposite sides of the carbon and giving a molecule a linear arrangement with a bond of 180 degrees. Okay, so if we look, carbon with the double bonds, those are going to be 180 degrees away from each other. Okay, they're going to be 180. That is going to reduce repulsion between the electrons. Okay, the shape of the 2 groups around the center is called linear. So it's going to have a linear geometry. Okay, or a linear geometry. This is the first one we're going to learn, a linear geometry. Remember I talked about why Lewis-Dot structure is a good structure to draw water, but it is a problem because this is not linear. And we'll talk about what geometry actually water has, okay? Central atoms with 3 electron groups. 3 electron groups are placed around the central atom. Repulsion is minimized by placing them as far apart. And that bond angle, the minimum, the maximum we can put them is 120 degrees. So the shape of the 3 electron groups around the central atom is what we call trigonoplanar. Okay, the 3 atoms are 120 degrees away. So that's going to be a trigonoplanar shape. Okay, another example of trigonoplanar shape, but it's going to be a little bit different. Okay, we have to be a little bit. It's going to be a little interesting. Is when you place 3 groups that are placed around a sulfur. So it's going to be a single bond to the oxygen, double bond to the oxygen, and a lone pair to the electron. Okay, electrons are going to cause problems, and they're going to be counted. Okay, so to minimize, yes, it looks like a linear. Usually we draw as a linear structure and Lewis dot structure, but those electrons are going to push the groups, and what we see actually is a trigonoplanar electron geometry with a bent shape, because the electrons here are going to cause that problem. Now we move to central atoms with 4 electrons. In a molecule like methane, 4 electrons groups are attached to each other around the central carbon atom. The repulsion is minimized by replacing the groups and the coordinates tetrahedral bonds of 109. Okay? If you look, this angle is not 109. Okay? This angle is a lot less, so it's going to be less space. So that's not, the Lewis structure is not going to reduce it. What we usually use is what we call the tetrahedral geometry. Tetrahedral geometry, you can imagine a tripod with an arm coming up. Okay? That's how and we're going to put those angles at 109. It's going to reduce repulsion, and it's going to increase stability. Now, again, we have 4 groups. Remember, I told you lone pairs we have put lone pairs, but they have been ignored. Not anymore. Lone pairs are going to count as a group. So what does that mean? We have a lone pair here. Okay. We have the lone pair and the 3 hydrogens for ammonium. Okay. They're going to be put again in the tetrahedral orientation, where you have the 3 tripod with the 3 feet with the hydrogen, and then you put the lone pair on the top and the arm. Okay, so you could think about it as trigonal bipyramidal shape and electron bipyramidal wedge resolution. So this is how we're going to put this particular geometry. Okay, so the central atom with the lone pair is going to be trigonal pyramidal. Okay, so that's what we're going to be able to do. The last one I wanted to talk is about water. Remember, I talked about water. Water is not linear. Okay, and there's a reason why it's not linear. Central atoms with 4 electron groups are water is one of them. You're going to have 2 electron groups attached to the hydrogen and 2 lone pairs. So that's going to give you a total of 4. The repulsion is minimizing by replacing the 4 groups and the corners of the tetrahedron, and the bond angles are going to be 109. Okay, so we put them in there, each corner, and that's going to be the tetrahedral. So that's going to push down, and that's going to have a bent shape. Okay. So again, to repeat, if you have 2 electron groups or 2 groups with 0 lone pairs, that is going to be linear. Trigonoplanar if you have 3 and 0 lone pairs. Once we start getting into a complication, okay, so electron group geometry, okay, and molecular shape, okay, trigonoplanar. When it starts switching is when you're going to have a trigonoplanar, but you're going to switch because you won't have 1 lone pair, so it's going to change the molecular shape to a bent. Tetrahedral is going to be tetrahedral for electron shape and molecular shape because they have 0 lone pairs. Tetrahedral, when you have 3 bonded atoms and 1 lone pair, then we switch the molecular shape to trigonal pyramidal. Okay, tetrahedral again, the electron group geometry is tetrahedral for water, but it has 2 bonds and it has 2 lone pairs, so it's going to switch it to a bent molecular shape. You might ask, why do we actually care about those shapes? Those shapes are important because we're going to be able to predict if a molecule is polar or not polar. You could usually do it easily by calculating with the chart, but it gets more complicated when you have a bunch of them and you have to start dealing with looking into stuff. So here we have what we call covalent bond. Okay, it's a molecule, can be polar or polar, non-polar or polar. The bond is a molecule. Its shapes determine whether the molecule classifies as polar or non-polar. So shapes are going to be important. Okay. Here we have a tetrahedral shape. Instead of chlorine, we have instead of hydrogen and chlorine. If we look at each bond individually, it should be polar. But now we have to deal with something else, the geometry. You see this one pointing up. You see that one pointing down. This one pointing down, pointing up. So those go down. So those are going to be pointing up in the opposite direction. Okay. So what does that happen? Those are going to cancel each other out. So the 4 dipoles cancel out. So that is going to be a non-polar molecule. So this is a non-polar molecule. Carbon tetrachloride, to repeat, is a non-polar molecule because the geometry is going to cancel them out. So this is where it gets interesting. Okay. Yes, we can calculate stuff mathematically, but now we have to deal with the geometry. Okay. Here we go with polar molecules. So you have HCl. This one is just 2 atoms, so it should be fine. It's going to be linear. Okay, so what we're going to see there is going to be polar because the dipoles does not cancel out. There's no other direction to cancel them out. So we have a polar molecule. HCl is polar. There's no way to cancel the geometry with geometry. Okay, remember I told you about water. Water is not linear. This is why it's important. We start drawing the electronegative arrows on it. Again, oxygen is more electronegative than hydrogen. Okay, the dipoles do not cancel out. That's what geometry is so important. Okay, geometry is so important. If we draw this linear, we cancel them out. But because it's, the electron pairs are going to push it down, that's why it becomes polar. Water is polar. The more negative end of the molecule is going to get reinforced. So polar molecules, in polar molecules as nitrogen, again, we're going to see that's what is important. Geometry is so important. We're going to see they're going to be pushing that direction because the nitrogen is more electronegative. So the dipoles do not cancel out. So ammonia, it is polar. Okay, it is going to be polar. So those geometries are going to be important. Ionic bonds are the strongest unattractive forces found in compounds. The most ionic compounds are solids at room temperature. Ionic compounds, sodium chloride melts at 801. Okay. Now we have to deal with a couple of things. We have to figure out if compounds have certain types of intermolecular forces. The first one we just went is ionic. Okay. So figure out do you have an ionic bond is going to be important. If you have dipole attractions, that's when you have a negative and a positive attractant from each other. In covalent compounds, polar molecules exert attractive forces are called dipole attractions. Have dipoles where positive charge and the dipole on attracted to each other. Okay, that is going to be important because that is actually going to affect melting points and boiling points. Now we have another force we call hydrogen bond. And hydrogen bonds are going to be limited, okay? But they're very important because they're very strong. Nitrogens, NHs, OHs, and HF are going to be the ones that are going to bond, okay? They're going to hydrogen bond. The negative charge, the positive charge are going to attract all the same molecule and they're going to interact. So they're going to have what we call intermolecular forces. What do you think? In DNA, this is what plays the biggest role in DNA. Okay. How does this affect melting points and attractive forces? The melting points of compound are related to the strength of the attractive forces between the molecules. A lower as a result of weak forces such as dispersion. Okay. Higher results when you have attractive forces such as bonding, hydrogen bonding. Highest when it's ionic compounds. Okay, those are going to be the ones that are going to be highest in melting point. Dispersion forces, I did skip it. This is where I want you guys to see. Dispersion forces are weak attraction between nonpolar molecules. Everything has dispersion forces. That's the minimum. Cause temporary dipoles, develop molecules bump into each other. Weak but possible for nonpolar molecules in liquids and solids. Here we will see some data to compare it. Here we have a couple ionic. Look at the strength of those ionic for melting points. How does it affect it? 1248, 801. When you have molecules only have hydrogen bonding, like water and ammonia, 0 and -78. Dipole attractions, HI, -51, -89, -115, and dispersion forces, -7, -109, 101, -220. So comparison of bond and attracting forces. Ionic are the strongest one. Covalent nonmetals are going to be followed. Then we have hydrogen, dipole, and dispersion are going to be on the weak side. So what we have learned about ionic compounds, ionic bonds, metals and nonmetals, positive ions, negative ions, charge imbalance, chemical formula, molecular compounds. We learn about covalent bonds, attracting forces, nonmetals, polar, nonpolar. We learned about how to actually learn the geometries, how to put those electrons, how does it affect shape and polarity, okay? Attractive forces, and how does it relate to attractive forces with dipole, hydrogen bonding, and dispersion forces.